Yeah, we're going to talk about that today.
I figured. I think I should probably wait till after class to actually try these.
Yeah.
It's bitten my butt.
But number 20?
Yeah.
Or 10?
That one. 10.
Number 10. So this is a question on a quiz that's due today, which, and we're going to spend a little more time talking about actually something like this today as well. So what this is there's a couple different events that you could observe about a person in the sample. And so there's 3 events. They have kids, or they could have kids. They could be enrolled in at least 12 credits. They could work at least 10 hours per week. Each person can make it either happen or not. So, and then I gave you some information. So they found that 44 students had children, 73 were enrolled in at least 12 credits, 105 were working at least 10 hours, 35 students had kids and were working at least 10 hours per week. So then my question is, what's the probability that a student has children or is working 10 hours per week? So this is a type of event. Both of these are types of events we're going to talk about today. So it makes a decent introduction because this is pretty much exactly where we're going to go at the beginning today. So you have this, you have kids and they work, and then you have this other event, kids or they work. Okay, and so these are what we call compound events. I ran out of room. Compound events. Okay. And we're going to talk about both of these and the one with the little exponent, the little c up top. So basically, you can have standalone events, but they can also interact in a lot of ways. And means that they have to what?
Go together.
Yeah, and means that they have to have both, right? Like they have to have both properties. Or is more general, one or, right, the other, or both is also okay, right? And so an or event is a lot more general. One's more restrictive, like you have to be both of those things. The other one's like, hey, you could be one or the other. If you're both, that's great, but you only have to have one of those properties. So, well, let's see. So we know that we're talking about kids are working, so that's A and C, right? So then 44 had kids. Yeah?
Yep.
And then we also know that 105 were working. Okay. But then I also gave you some other information, which becomes important because 35 students were doing both. Right? So one thing I'm going to show you in a second is when we think about compound events, one way to think about them is using Venn diagrams, which is something you may not have used since like English class, but I don't know when the last time you used a Venn diagram is. But basically the idea is you have two groups where there's overlap. So when we say that 35 students had kids and were working, see those 35 students, they fall in both groups. And so these 44 students include those 35 students, but these 105 students also include those 35 students. And so if you just add up these two numbers, you're going to double count people. So you're going to double count the people in the middle. And they don't double count because they're not double people, right? So what you have to do is you have to take into account the fact that they overlap. And so the numbers out here, like this whole circle should add up to 44, which only leaves a certain number left here. And this whole circle should add up to 105, which only leaves a certain number of events there. So, yeah, right. Yeah. So you just have to take that overlap into account. And that's actually exactly what we're going to talk about right now. So essentially what happens is that if you're trying to calculate the probability of an OR event, you can add up the two events separately, but you have to recognize that you may have double counted the overlap. So you might have to subtract that out. So, all right. And we're going to do another example. We'll do an example of that one today too. So give that one a try now. Okay. So let me just go through those events, and then maybe if you want, if we have time, we can come back and look at one of the other ones too if you had other questions about this. Okay. So let me just run through the three types of compound events that we'll consider in this class. So we were talking generally about probabilities. I kind of talked about what the law of large numbers implicated. And then I showed you some probability notation. And so the last examples we were looking at, we were just looking at some general events, the fact that events can consist of multiple outcomes, you know, and then depending on how many outcomes an event had, that's how you determine its probability. Because the probability of an event occurring is just the ratio between, you know, how many ways can you have the event divided by how many events are in the sample space. And if you're dealing with a situation where you know what the sample space looks like, then everything's nice and easy. You can calculate the theoretical probabilities. It's not always so straightforward, but these examples have a situation where you can see the whole sample space. So this is what we were getting at there. So other types of events. So one is called the intersection. So we say that the intersection of A and B, right? So that's all the it shouldn't be events, outcomes that satisfy both. Both A and B. Okay. And again, so we use sort of Venn diagrams. So it's like if here's all of A and here's all of B, the only people that satisfy both A and B are the people that have both qualities. Yeah? Yeah. And generally, it's normally we just denote it like this, you know, just A and B. There's like logical operators. Sometimes the intersection is written this way, but that's more of like a logic, or maybe if you took like a philosophy class or a logic class or something, they would use this notation to represent intersection, but I'll just use it that way because it's way more simple. Just to write and. All right? So far, so good? All right. So like here, we can look at some a simple example from the cards we were talking about. So if B is that the card is a heart and C is that the card has to be a face card, then what does B and C look like? It has to be king. Yeah, it has to be a heart and it has to be a face card. So what's in there? Has to be a heart and a face card. This one's the more restricted one. There's going to be not 4 cards.
But he's saying like 4 is hard, right?
Are you saying there's going to be 4 cards there? Or are you saying?
Yeah, possibly.
Are there 4 cards there?
4 face cards.
I think there's only 3.
Oh wait, 4. Yeah,
It doesn't count as a face card. Yeah. Yeah, there's only going to be 3 there, right? So it has to be a heart and a face card. So the only thing there is going to be like the Jack of Hearts, the Queen of Hearts, and the King of Hearts, right? Yeah. So there's only 3 outcomes. So then the probability of seeing both at the same time would be 3 out of 52, which that would reduce to, is it reduced? Is 52 divisible by 3? 52 is divisible, not divisible by 3 because 5 plus 2 is 7. Okay, so there you go. We could make it a decimal though. There you go. So it's like 0 point, you said 0, 5, 6, yeah, something like that. So either one of those would be acceptable answers, okay? So the and means that it has to satisfy both. It's more restrictive. So it's like the intersection is going to be no bigger than the smaller of those events, right? So you can't get any, you're not like including extra things. It's usually more exclusive. The union, though, is the other one which we were talking about, and then that's the or. The union of A and B, which we often denote A or B, are all the outcomes satisfying one or the other. So we'll say satisfying at least one of the events, A or B. Okay. So if you think about that from the Venn diagram standpoint, it's like if this is all of A and this is all of B, then the union, if you're in A, you're good. If you're in B, you're good. If you're in the overlap, you're also good because it's just one or the other, at least one of the events. So basically it's like everybody's in. Like you all, so this is A or B. Okay? And so normally that's the way we denote it, is A or B. There is some union, there is some symbology that we use in like a logic or a math setting. Sometimes it'll be like the U, the cup, or whatever. It's called A union B, but we'll call it A or B because it describes the situation better. One or the other. You choose. Both is cool too. Yeah? Okay. So, everybody good with that? Okay, so then the like this one, so last time we looked at had to be a heart and face card, but now I'm being less restrictive. I'm saying it could be a heart or it could be a face card. So what's in this event? All the hearts are in, yeah. And then all the face. So what happens is first, right, you get the, so like the ace of hearts, the two of hearts, all the way up to the jack of hearts, queen of hearts, king of hearts. So those are all in, right? Now, what else do we need to toss in?
The rest of the hearts.
Yeah, well, the rest of the face cards, because you got all the hearts. So now we got to throw in all the face cards from the other suit. So then it would be like the jack of diamonds, the queen of diamonds, the king of diamonds. Then you throw in the jack of spades, queen of spades, king of spades, and then the jack of whatever's clubs. Thank you. Queen of clubs, king of clubs. Okay. Now, what's the probability of B or C, though? So how many events are here?
23?
Yeah, because we have close, I think. How many are in the hearts?
14?
It's 13. Because, yeah, right. It's 13 cards per suit, right? I knew you were just off by one. I couldn't figure out why, though. But that's why, because 13 per suit. And then how many extras do we have to toss in?
12.
Well, there's 12 face cards, but we already had 3 of them thrown in with the. This is the same thing as that quiz problem. Okay, so we only had to throw in 9 additional outcomes to be in B or C. Does that make sense?
Yeah.
So we have to throw in the rest of the face cards, but these face cards were already there. So there's some overlap in them, and so the probability of B or C is going to be 22 out of 52, which is like 11 out of 26, or if you approximate that, what does that come out to be? You need 4 decimals.
42308.
42308. 2308, so maybe 0.4321 if you round. 4231. Or was it 4321 or 42?
It's 423.
Did I get it wrong or right?
You got it wrong.
Okay. Sorry.
0.42308. Then we round that up.
Wait, no, so did I get it right?
Oh no, 4231.
423.
Instead of 4321.
Yeah, that's how I had it.
Oh, I thought you had it the other way.
Well, then I was questioning myself. That's right. Okay. So what happens is this is what happens in the problem with the question with the different, like, do they have kids or do they work? Because in the Venn diagram, there's this 3, like in this example, there's this 3 card overlap. So there's 13 hearts, but 3 of them are in the overlap, so only 10 of them are over there, right? And there's 12 face cards, but 3 of them were already in the heart overlap, so there was only 9 more that we needed to tack on. Okay. So another way you could have figured that out is you could have figured out, well, the number of hearts is 13. The number of face cards is 12. So if you just added those up, you would get 25. But then if you recognize that there's 3 in the overlap that I double counted, you'd have to take those 3 away because you double counted them, and that's how you'd get to 22. So you don't actually have to list out the sample space to know that. You can just add up the two events and then subtract off that overlap once, recognizing that you would have double counted it. Yeah. All right. So you can have an and, you can have an or, and they're different. And then we'll also work with something called the complement. So if you have an event A, so for an event A, the complement of A, which we denote with that symbol. It's like an exponent, but it's just a C up there, A complement. Is the set of all outcomes that don't satisfy A. Not. It's like the opposite. Okay. So another way that this is sometimes written is, so I'll just say alternate notation. Okay. So this is, well, I'm going to use this one, A complement. Sometimes you'll see it written as A prime. Sometimes you'll even see it written as just, some people will just call it not A, because that's literally what it is. And so from a Venn diagram standpoint, if you have an event A and you're in the sample space, the complement is literally everything else. It's the opposite, more or less. Okay?
So if we want to find AC, it is literally everything but A.
Exactly, yeah. So that's why I actually kind of like this notation, calling it not A. It's not as common. So this is the most common way that complements are denoted, so that's why I use it. But you can call it not A. And it makes sense to call it that because that's literally what it is. So, and the reason that we might consider complements is we'll find out there are situations where sometimes it might actually be easier to calculate the complement probability than the actual probability. And they have a special relationship to each other, because together they make up the entire sample space. So, yeah.
What if it's both A and B?
What's the complement?
Yeah, like, would that be part of that?
Oh, we could go down that road. I don't really know if we want to go down that road, but you can, yeah, I mean, if you took like a logic class, or maybe even they might get into this in like philosophy 101. I don't even know if we teach that class. But yeah, you can have complements of compound events. But then you just have to think about, okay, well, what does that mean? So if this is A and this is B, the complement is everything in the middle. And so A and B is everything in the middle. And so the complement of the intersection is all this stuff, So we're not going to get that detailed into, what I'm saying? So the complement of the intersection is just everything they don't share. So, but we won't go that complex. So, okay. So you don't have to necessarily think about that. All right. All right. So like with ours, if B is the event that the card is a heart, then what is B complement?
Everything but heart.
Yeah, everything's all the cards that aren't hearts, right? So it would be all of the diamonds plus all of the spades plus all of the clubs. And so together, how many cards would that be? Yeah, that would be 39 cards, all the other ones basically. And so the probability of B complement would be 39 out of 52, which I think reduces to 3/4, yeah, because it's the other 75% of the deck, which makes sense. Because what's the probability of B itself? It's the 1/4, 13 out of 52. It's 25%. And that's how it should be, right? Because together, an event and its complement should make up 100% of the sample space. So, all right? Okay. That's the notation in the quiz. So when you get to the other, I don't know if I kept the quiz running this time. Oh yeah, here it is. So when you get to like question 11, you're talking about the complement event. It's saying basically the opposite. You know, it's everyone else. So B is all the people that are enrolled in at least 12 credits. So the complement would have to be all the other people, and I want you to tell me how to best describe all those other people. All right? That's what the C means. Okay. So, not all events, necessarily overlap, and so that's something we call mutually exclusive. So then we say that two events are mutually exclusive if they share no common outcomes. In other words, if they do not overlap. If no common outcomes. All right. So picture-wise, that would be like A's over here, B's over here, and there is no overlap. In other words, there is no A and B. Okay. So just means that they can't. In other words, another way to think of that is they can't happen at the same time. So, all right. All right. So then, this is kind of like the one the demographic information, but here's a couple different events that you could observe in a survey. Then they said, okay, full-time, older than 30, taking one course, has kids, minor. Which ones of these are mutually exclusive?
B and E.
So B, that they're older than 30, E, that they're a minor. So yeah, we would say that B and E are mutually exclusive. That's true.
A and C.
And then probably also A and C are mutually exclusive, being a full-time student and taking only one course. Because I think to be full-time, you have to have at least 12 credits. And I don't think we have any single 12-credit courses that I'm aware of.
That'd be cool if there was, though.
It could happen, I don't know. I wouldn't be surprised, honestly. But I don't know of them, if they exist.
I would take it.
Well, if it existed, it'd be in some really specialized program. It'd be like an agriculture class or like a welding class or something like that. I could see it, so. All right. Make sense?
Yep.
Just means mutually exclusive means they just can't happen at the same time. I don't think there are any other mutually exclusive ones there.
We call that 0.
So, what's that? You good? You sure? Okay.
Like 0, right? Like, you know how we do like the 1 is a whole, but you can add them up, it'd be 0 since. You explained it earlier, but I don't think it relates to this.
Well, actually, it kind of does, but I think I know where you're going.
Okay.
Okay, so now this is the thing. So up here, when we were doing the face cards, I was telling you about how there's theoretical probabilities. So if you can envision or you can actually understand the entire sample space, all of these are theoretical probabilities. 25%. You should get a heart about a fourth of the time when you draw cards, right? Long run averages. But the theoretical probability doesn't actually necessarily exist. Or if it exists, you would never know it. Like, what's the probability that a CVC student is older than 30? Like, is there a theoretical probability? Not really. You could say there is some percentage of students that are older than 30 right now, but the problem is what? Even if you could stop time and figure that out, what's the problem? It's going to change because in a couple days, somebody is probably going to turn 30, and some people are probably going to drop out, and other people are going to enroll, and so it fluctuates, right? And so there really is no theoretical probability of someone being older than 30. You could get pretty close to it if you did a really good sample and you figured out how many were older than 30, but even your number is going to be off. So So we're oftentimes all we have to work with is empirical probabilities. So one way that we can look at empirical probabilities is we called them relative frequencies back when we initially talked about frequency tables and sampling. But you can think of relative frequencies almost like probabilities, because if I took like a sample, so this came off of some data where they looked at self-identified religion, and these were the categories, and these were their percentages. If you're going to go out and you're going to randomly select a person from the population, you can think of these as the probability of seeing people in those categories. So if I'm just going to randomly take one U.S. citizen, then there's a 51% chance that that person I observe is going to be a Protestant. And there's a 21% chance that they're not going to claim any of these four. Right? Okay. And in this case, so let's say that A is that they identify as a Protestant. Let's say B is that they identify as a Catholic. So what would be the probability of A or B?
Add those up.
Yeah, because here, right, it's A or B, Protestant or Catholic. And so we know how many were Protestants. We know how many were Catholics. And so we can just add them up. 0.752, right? Okay. High chance that you're going to get a Protestant or a Catholic if you did a random sample. Now, in this case, do we have to worry about any overlap? We don't have to worry about double counting people because nobody was double counted in either of these categories, right? They picked one or the other, or right. So there is no people there is no overlap essentially. So self-identifying as Protestant is mutually exclusive from self-identifying as Catholic. You got to pick one or the other for the survey. Okay. What about the complement? What's the probability? What is this? This is a probability of basically not Catholic.
76.9%.
How do you know?
Because I subtracted 0.29 from 1.
Yeah, there's two ways you can calculate it, right? You could just add up all of the non-Catholics, right? So you could take all the Protestants and add in all the people who said Jewish, add in all the people who said Mormon, and then add on all the people who said something else. Okay, and what would you get? You would get 761. The other way to think about this is, well, complement events make up the whole sample space. So you could just say, well, it's got to be the opposite of 23.9%. So you can just do 1 minus the probability of Catholic, right? So this is what I was talking about when complement events is like, why would you ever care about the opposite of what you want? The reason is that sometimes the opposite of what you want is less complicated than what you actually want. There's a lot of people that are not Catholic. So I'd have to go find all those people and add them up. This one's a pretty simple example because adding up 4 numbers is not that hard. But it gets way more complicated. It can get way more complicated. So the complement strategy can really work in your favor when you're trying to calculate probabilities. Does that make everybody okay with those numbers? Everything here? Does that make sense? Any questions about these ones? Okay, this is two. So what I'm looking at here is these are two special types of relationships that we talked about. In the first example, we were looking at events that were these two things were mutually exclusive. And then in the second one, we were considering complement events. And so you can see some relationships forming between like compound events and probabilities. So for complement probabilities like the one we just observed, in general, if you take the probability of an event and you add the probability of its complement, we saw this with the cards, right? The probability of an event and the probability of its complement should always add up to 1. And then we take advantage of that property. So if you're trying to calculate the probability of an event, you may be able to get there quicker or more efficiently or with less error by just doing 1 minus the complement. So that's one way that we use. This is like one of those. We're going to get quite a few. Well, we're going to get some formulas in this chapter, and so this is one of those. Okay, so this relationship always holds true. So if you know the probability of the event, you could always get its complements. The other thing, what did I want to do? Oh, okay. Yeah, I'll get back to the mutually exclusive thing. I have a couple other examples I want to look at. Okay. All right. If you go back to the dice rolling, I rearranged some of these slides from what was originally posted, but and I had a couple examples. So let's say that you're rolling 2 6-sided dice. What's the probability that the sum of the dice is not 7? Well, there's two ways to approach that, right? So essentially, you could think of event A as, rolling a 7 and then not a 7. So you could calculate the probability of not 7. It's not that hard, right? You just got to add up all of those things, right? And then add up all of these things. And then there was my typo again. But add up all of those things, right? And then how many of them are there? I don't know. There's 30 of them, I think. So you could add up all the non-7s and you get 30 out of 36. And then if you convert that to a decimal, what do you get? Say rounded to 4 decimal places. What does that come out to? 30 out of 36? 8.33333?
Yeah.
So it's like 0.8333. So that's the answer if you just add up all the non-7s. But another way to think about this is it's actually a lot easier just to know that, the probability that you don't roll a 7 is really just 1 minus the probability that you do, and there's not that many, 1, 2, 3, 4, 5. There's only 6 of those, right? And so you could calculate the probability of a 7, 6 out of 36, and I would be willing to bet it's probably 0.166666 repeating, right? So you could this is just the probability of actually rolling a 7, and then you just subtract it from 1, and it's going to get you to the same solution. So, all right? So you think, okay, well, which one's easier to calculate? And I'll just go with that one. And then take advantage of complement probabilities. All right. So with the example I did up here, I was telling you, these are mutually exclusive, Protestants and Catholics, at least for the sake of that survey. That's not always the case, like the one in the quiz, where you have events that are not mutually exclusive. There's overlap. So here's another example. And we don't have the sample space here, so we're just going to have to work with percentages, which makes our lives a little bit harder, but we can handle it. So let's say the Census Bureau says that 51.4% of the population is female. 10.4% has been divorced at least once. 6% of the population are females that have been divorced. What's the probability that a randomly selected citizen is either female or has been divorced? So one or the other. So what do we know here? So we got a 51%. That's the what? That would be P of female. So one thing I do when I'm tackling probability problems is I like to start giving my events some names. So we'll just say, let's define F, female, and D, divorced. Makes sense because they match. Okay. So then what we have there is P of F. That's our probability of female. What do we also know? Probability divorce, right, is 10.4%. Now, what's this number right here, this 6%?
That's subtract that 1 time.
Yeah, it's 6%. What does it describe, though?
It's overlap.
It's the overlap, right? It's the probability of female, and divorced. Okay. So what you have here is you have a situation where F and D, these are not mutually exclusive in this case. Because there are people that are both. Right? So then if you think about, the Venn diagram, right here, there's 6% in the middle. So if you just take all of the females and you add up all of the D4Cs, then what have you done?
You double counted.
Yeah. So in here, what you will have done is you will have double counted the 0.06 overlap. So what do? Yeah, you just compensate for it by taking it out once. All right? And so you add those up, you get like 61.8%. But there's people that got double counted in there, so you take away the 6%, and then what do you get?
55.8.
Yeah. Like that. All right. Essentially, what it was is we took the probability of being female, we added in the probability of being divorced, and then we recognized, oh, these aren't mutually exclusive. There was overlap, so we subtracted the probability of being female and divorced one time to get rid of that. All right. And this form right here, this is the form of what we call the general addition rule in probability. So if you don't have the sample space, sometimes you have to work with formulas because I just don't know the sample space. So in general, this always works for two events, say A and B. In our case, we call them D and F, but the letters are irrelevant. For any two events, A and B, if you want to take the probability, if you want to get the probability of A or B, so in other words, we're trying to figure out the probability of A or B, it could be one or the other, you can take the probability of A, all of this, and then you can add in the probability of B, all of this, but you can see from the picture in our last example, you'll double count the middle, so you compensate by taking out the intersection one time. And this is the general addition rule, and that's what's going to maybe help you on that question that you asked about. So, add up the two events and then subtract off that overlap once because you double counted.
So you know how the first time we did, so if you had the 51%, right?
Yeah.
In A, and then you had the 10.4 in B.
Yeah.
Wouldn't you do the 51 minus 6
You could.
for A? But you don't get the same percent.
Well,
Like that's how we did it like in the first example you had showed. Maybe I just...
Oh, no, I see what you're saying. You want to take the 6 out of the 51.4 and then take it out of the...
oh, well,
and
no.
That's left over after that, then you add them up.
Yeah, but see, okay, yeah. But
So
if
is
you...
that different?
Well, if you do it that way, see, I understand what you're saying. If you do it that way, my picture's not... Well, if you take away the 6%, and that would leave you with 4.4 here, and that would leave you with like
Oh,
0.454 there. Yeah, if you want... In general, I'm not that worried about these numbers, but notice that if you add those up, you still have to add the overlap one time, right? So if you do it, it's a little more complicated actually to do it that way. I was actually just drawing it that way to show that overlaps in both groups, and so it changes the number, like it changes your counts. But yeah, you could break it apart. Yeah, there's 4.4% are female, or are divorcees that are not females. That's the number of male divorcees.
so then you don't take off the 6.
Right, and
You
then
would just
you don't
do
have
that
to,
just
right?
show us.
Yeah, I mean, you would do that if you actually cared about those numbers. So what is 0.454? That's females that have not been divorced. This is divorcees that are not females. This is both. But you don't need to break it apart that specifically. you can just add up these and then add up those and then just take the intersection out once. It's easier that way, probably. It's less work. Yeah.
General.
General addition rule. And it just, the reason it's called the general one is because there's a special one. But the general one always works. And it takes into account the overlap. Sometimes there's no overlap, though. So then you don't have to subtract all. If there's no overlap, you don't have to subtract it. Right? So, okay. So here's an example where, so it says 40% of CVC students claim Hispanic or Latino ethnicity, 4% of students claim Asia Pacific Islander ethnicity. What's the probability that a randomly selected student claims one or the other? Right? What's the probability of one or the other? It's just going to be, right?
They're mutually exclusive.
Yeah, because what happened here is that these two events, I mean, I guess they don't have to be, but I was assuming for the sake of when you fill out your demographic information, if you consider these mutually exclusive, like there is no overlap, you have to claim one or the other, like your primary ethnicity, then you don't have to worry about an overlap, right? Because, see, like, so this is like the probability of Hispanic, Latino, this is the probability of Asian Pacific Islander, and then technically, according to the rule, we should be subtracting out, right, that overlap, except for what's true about this?
There is no overlap.
There's nobody there, right?
Shouldn't that be and?
Yeah. Sorry. Yeah, I was thinking, if you're going to calculate the probability of, like, Hispanic or Asian Pacific Islander, the rule says you should take Hispanic plus Asian and then subtract off the overlap, except for in this case, there is no overlap to take away. So if they're mutually exclusive, then you don't have to worry about it, and that's the special case. So that's the special addition rule. So if A and B,
Because they can't, well, for the sake of they won't get picked.
yeah, so that's just assuming. I don't actually know if that's how the demographic collection works at CBC. But if two events are mutually exclusive, then if you're trying to calculate the probability of A or B, you can just take the probability of A and add the probability of B, because technically you could try to subtract off the probability of the overlap, but you don't have to worry about it because since they don't overlap, you're not going to there's no double counts, basically. So mutually exclusive does matter. It's an important thing to think about because it could affect how you have to handle probability calculations. All right. But the general rule, we call the general rule because it still works in the case of mutually exclusive. It's just the probability of the overlap is 0. So there's nothing to subtract. It just disappears. All right. So in general, another thing to notice here is, I'm going to put this off to the side actually, is in general, you see that we're calculating OR probabilities. So if you're calculating OR probabilities, okay, you notice that basically those are always, in some way, they're going to always involve addition. Because it's like you're including, in an OR probability, you're including more people. You're making it more broad. And so they're always going to include addition, but you just need to decide whether the two events are mutually exclusive or if they're not. Because if they're mutually exclusive, it's just straight addition. But if they're not, then you have to subtract the overlap out. So, but it's addition either way. But you do need to ask yourself whether they're mutually exclusive or not if you're trying to calculate OR probabilities. All right? Sure. All right. Let's look at some other scenarios, how these ands and stuff can work. So back to contingency tables. We saw these last week. comparing two qualitative variables, right? So the numbers in the middle, those are things, those describe two things happening at once, right? So 18 describes people that have master's degrees and they took their kids on field trips, because this was comparing their highest level of education and whether or not they took their kids on field trips for some elementary schools in Tennessee, right? So 51 teachers total, and then the margins, those only describe one thing. Yeah? So like 32, that's just how many teachers did what?
Total, yes, field trips.
Went on field trips, right? 32 is the total number of teachers that did field trips. And then so we can start, we looked at some percentages before with the tables that we saw last week, but we could think of probability. So it's like if you're going to randomly select a teacher from this sample, then what's the joint, we call it a joint probability because it's two things happening at once. What's the probability that a teacher has a bachelor's degree and they took their student on a field trip?
50%.
Bachelor's degree and took their students on a field trip. So how many people, so the probability, so in this case, so I'm going to say bachelor's and field trip, right? In this case, we have the sample space, so we don't really need to worry about formulas. How many of those were there?
There's 14, yes.
Yes.
28.
And so the definition of probability is, well, how many meet that requirement? 14. And how many teachers am I drawing from?
51.
This one is, should it be 51 or 28?
51.
Is it 51?
That's just teachers in general.
It's just,
Oh,
yeah,
teachers.
it's just that any teacher, right? So I'm not like giving you any conditions. I'm not telling you that a certain thing has to happen or anything like that. I'm just saying in general, if you just pick a teacher out of this pot, what's the probability that they have both attributes?
27.4.
It's 14 out of 51, which is that the decimal?
Or 0.275.
Give me 4 decimals.
Oh, 0.2745.
4 or 5?
Yeah.
Yeah, like that. So other people get that?
Yep.
Okay. So there's about a 27.5% chance that they're in that category. They have both attributes. And the and is more restricted, like they have to have both. Okay. What's the marginal probability that a teacher has a bachelor's degree in general?
20.
Yeah, and just a general, it's not two things happening at once, it's just one thing. The probability that they have a bachelor's degree overall, that would be the 28 out of 51 total.
54902.
54902, something like that. So about a 55% chance you end up someone with a bachelor's degree, right? So you can use, this is another example of, if you have the sample space, don't try to use complicated formulas, because I have the table there. I can pull these probabilities out of there because I understand what the sample space looks like. Okay. All right. What you were thinking of, though, is some people want to divide by 28. But if you, like on the first one,
I was specific to just bachelor's.
yeah, see what happens, and we did this when we looked at the contingency table last week. We didn't divide by the total, we were dividing by like the sums at the bottom of the columns. But that's actually a different probability. Because like if you did 14 divided by 28, what would you be calculating?
50%.
It'd be 50%, but what does that describe?
Describes the amount of yes to field trips in the bachelor's.
Yeah, it's among teachers with bachelor's degrees, there was a 50% chance they took them. Like if you restrict yourself to just teachers with bachelor's degrees. And that's an interesting, that's not a useless probability.
Is that and still?
No, that's a different type of probability, which we're going to talk about now. Okay. I'll give you another example. So, let's say that I'm going to offer you, let's say I'm going to let you guys gamble, all right? Let's say we're going to play a game, and I'm going to roll 2 dice, and if the dice come up equal to, like the sum is equal to 7, all right, then I will give you 5 free points on your last exam. And if the sum is not equal to 7, I'm going to take away 2 on your last exam. Or let's say I'll take away 1. Let's say I'll take away 1, right? So you can either earn 5 if I roll a 7, or you can lose 1 if I don't. All right? So then you have to decide whether or not you want to play. One thing you should consider if you want to play that game is you should probably figure out, well, what's your odds of winning? Or your probability.
17.
Well, here, this is just over. I'm going to roll them. 7 or not 7. You win or you lose. What's the probability that you win that game? What's the probability of A?
1/6.
Yeah, so how many ways can you roll a 7? 6 ways out of 36. In other words, you have a 1 in 6 chance, which I think is 0.16666. 6 is repeat forever. So almost a 17% chance that you win. You get 5 points if you win. You lose a point if you don't win.
That also.
1 over 5.
Do you want to play?
No. Not 60%.
You can play as many times as you want.
You have a lesser chance.
Well, until you run out of points. If you run out of points, then if you hit 0, you can't play anymore. It's like the casino. If you run out of money, you can't play. Right?
That'd be fine. Can we just do a test like that?
Now, the question is actually, and this is something we'll talk about in the next module. So that's a payout ratio, right? So I'm offering you like a risk to reward ratio, like 5 to 1.
I wouldn't do that.
Okay? But I'm also not giving you even odds. And this is how casino games work, right? The worse the bet, the bigger the payout. Because they're going to try to tempt you to take low probability bets by offering you high payouts. Now the question is, in the long run, if you play this game, do you think you'd run out of points or do you think you'd gain infinite points?
Run out of points.
It depends on the payout. I suspect this one is not in your favor because I'm offering you a 5 and 1 payout, but I'm only giving you like a 1/6 chance. You would want, right? Does that kind of make sense? So there's something called expected value. There is an expected value to this bet, and we'll talk about that more in Chapter 5. But just for the sake of this, I suspect you'll probably lose in the long run on this game. I don't know for sure, but that's my suspicion. If I betted a better bet, like I'd give you 10 or you lose 1, then that actually might be a good game for you to play because you'd recoup your losses often enough with that payout. Anyways, okay, now let's say I'm going to make the game, maybe I want to make it more interesting. And so I roll the dice, and I agree that I'll tell you whether the dice is odd or even before you have to make your bet. All right, I'll tell you whether the sum is odd or even. So let's say I roll the dice. So let's say up here, it's like, okay, do you want to play? You say, I'm not that sure. And so I roll the dice, and I'm looking at them, and I tell you, I say, okay, well, I'm going to tell you right now that the sum of the 2 dice is odd. So does that change whether or not you'd like to play the game?
It increases your odds.
Yeah, what happens is our probability goes up. Why?
Because we get rid of all the
more
evens.
odds.
Yeah, because now our denominator is no longer 36, right? Because all of the even numbers, that's a 7 again. I made the mistake all the way through the slides. That's all right. All of the even numbers are out of the equation. Can't happen. So how many options do you have? Yeah, I just eliminated half the options. You're down to only 36 options, but how many of them are winners?
6.
All 6 of these are still winners. So what I did is I increased your probability of winning to a 1 in 3 chance. And so I've increased your probability to a 33% chance. Basically, I've doubled your odds of winning by giving you that hint. So would you play that game?
Yeah.
Yeah.
That one actually is probably a good bet. If I'm going to pay you 5 to 1 and you have a 1 in 3 chance of winning, you're probably going to come ahead in the long run. All right. So what I'm getting at here, and this has to do with like the bachelor's degrees or like what we're talking about, high school degrees versus employment level, is certain events can affect the probability of other events. So the dice being even or odd affects the probability of rolling a 7. Because, for example, if I told you they're even, what should you do?
Don't bet.
Yeah, what's the probability?
0.
Yeah, there's 18 numbers and absolutely none of them are 7s, right? So if I'm willing to play the game that way, it's actually a pretty good game for you. Because if I tell you it's even, don't bet. And if I tell you it's odd, take the bet. Because even though you're going to lose sometimes, you'll probably come out ahead in the long run on that one. Okay. these are examples of what we call conditional probabilities. They're probabilities, but they're conditioned on something guaranteed to, or like something that had to have happened. So, we say the conditional probability of an event A occurring given an event B has or will occur. So the notation we use for this is the probability of A given B, and the little line, that little up and down line, when you see, when it's in pairs, it usually means absolute value in math, but when it's just one, it usually means given, or subject to, or, so this is how you notice this, probability of A given B. That's how you, so what you see is like, in the last example, so like A was that you roll a 7, and say we define B is that you roll an odd number, right? Then the first probability that we calculated, overall your probability of rolling a 7 was that. The second one we calculated was actually a conditional probability. Like that. So, okay?
So like, let's say it's like given B.
Yeah.
It's like, it's a 1 out of 3 chance. You just like multiply or divide the fractions. Like, as rolling a 7 is like 1 out of 6, and it's like you do something to make it to improve a 1/3 chance.
Yeah.
Would you divide the fractions? So it'd be like,
Yeah, so it depends on, okay, what you're asking is how do you handle conditional probabilities when you don't have the sample space?
yeah.
And it's yes, the answer is division.
Okay.
Yes. Well, we're going to there's a formula for it. Yeah. We're going to get to that formula. Are we out of time or something? Oh, yeah, we are. Okay, so we'll look at this one again. That's where we'll pick up tomorrow. But yeah, we'll look at that. And then when you don't have the sample space, you're going to have a formula. But we'll talk. But it is division.
Okay.
Yeah, you take the probability of the overlap and divide it by the probability of the given condition. And then the denominators cancel, actually. And then, it works out.
I like this.
Yeah.
I feel like I hate it when you explain it.